Okay, let's see. It's being very uncooperative today. Now, hopefully that's working. All right. So today we're going to talk about oxidation reduction. Here, possess. Let's trying to close this other instance. Oops. There. Okay. So there's reading in several different chapters, bits and pieces. That part of chapter 3, small section in chapter 13. And that's for today and part of next time. Probably we're not going to get through what I plan to get through today because we just had this other conversation. But we're going to do these two topics this week. So this will probably spill over. But this is redox, environmental redox, and this is organic chemistry. So I also prepared a little video about total chemistry review stuff, about oxidation states, about half reactions, and the NERTH reaction. The slides are in this presentation today, but I'm going to skip over them. And as I mentioned to you by email yesterday, if you don't remember what an oxidation state is, how to figure it out, what the oxidation state rules are, what is a half reaction, how to write a half reaction, how to do algebra with half reactions, it's all in that video. And I want you to watch that first before you ask any questions about oxidation states or half reactions. But if after you watch that video you have any questions, then feel free to ask me, you know, so that you're completely up to speed on the concept of redox, half reactions, oxidation states, and the NERTH equation. Okay. So redox state, it turns out, which remembers how oxidized or reduced something is. It's one of the kind of two main master variables for natural waters on the planet. It also happens to affect non-natural waters, and it affects rocks as well. Okay. For instance, the conversation we were just having about the fraction of iron in lava, that is iron 3 versus iron 2, is a measure of the redox state. In a situation where a magma comes from a very reduced environment, all the iron will be as iron 2. In a very oxidized environment, all the iron would be iron 3. In reality, it's some mixture of the two. Okay, but when we're talking about natural waters, which is what we're focused on for the first part of the semester, the redox state is largely a function of whether or not there's oxygen present. Where does oxygen come from at the surface of the earth? Anyone? Exactly. So it's life. Oxygen is produced by life. It's also consumed by life, respiration. So this is a proxy for how much biological activity is happening in an environment. There can be other reasons besides life that can affect redox state. So I want to give you the implication that that's the only thing. But in natural waters, especially near the surface of the earth, it's the main thing. Okay, so redox, along with pH, how acid or base the water is, are the two things that control almost everything about the chemistry of a solution, an aqueous solution. There are other things that we've already talked about, things like how much organic matter is present that can change the solubility of certain low solubility elements, active particles, pressure and temperature would start to come to bear when we get down into the deeper parts of the ocean or we go into groundwater situations. Those variables play different roles in different settings, but these two things are like what we call the master variables, because they control much about the behavior of many really important chemicals in the environment, particularly because as a function of how oxidized or reduced the environment is, some chemical elements change how soluble they are or aren't in water. So when they change their solubility, it changes the makeup of the water as a function of how oxidized or reduced it is. So it turns out that this is something that's really critical. So this is a depiction of photosynthesis in the most simplified, boiled down, non-realistic, schematic, I just want to emphasize with the exclamation point, this is schematic way, water and carbon dioxide, the whole series of steps are turned into carbohydrate and oxygen. That's photosynthesis. In respiration, what we all do is the reverse, right? We take in oxygen, we break down the carbohydrates that we consume, and we emit carbon dioxide in water. And that's just like a straightforward interaction. In fact, and I put this in here, if we write out a more realistic version of this equation, which we'll do later in the semester, you'll see that photosynthesis consumes a little bit of hydrogen ions. It's not stoichiometric. It's not, 1 mole of this consumes 1 mole of that. It's more like about 138 moles of that consume about 16 moles of that. But we'll get to that fraction later. But in any event, when we do photosynthesis to make an environment oxidized, we make it like a little bit less acidic because we're consuming some hydrogen. And when we do respiration, okay, we're making the environment a little bit less oxidized because we're taking away the oxygen and we're adding a little bit of hydrogen, so we're making the environment a little bit acidic. Okay, so for instance, if we were in water, living and breathing, and consuming oxygen the way we do, we would be slowly acidifying and reducing the water by being present. And in many balanced environments where there's sufficient nutrients, fertilizers, if you will, to make this forward reaction happen, all of the reduction in oxygen that happens from respiration is balanced by photosynthesis. So we never see the oxygen concentration go down. Right, so in the surface ocean, surface lakes, surface waters that are changing with the atmosphere, that are unperturbed by human activities and have kind of normal biological and biochemical cycling, we should see a balance between these two things. However, if we go away from the surface of a body of water that can exchange with the atmosphere, which has a huge amount of oxygen that it can exchange across the surface layer, we get to deeper in the water, we can find situations where there's more of this back reaction happening than this forward reaction. There's a whole bunch of different reasons for that. One of them is there's just not enough light, right? If we go down deep enough into the ocean, even just 100 meters down, there's already a lot less of this forward reaction happening. There's still plenty of the back reaction. There's still plenty of animals respiring, but there aren't so many plants producing photosynthesis. That's one way. Another way is to go under groundwater, down below the surface where there's no light. Another way is to go into a body of water where there's just not enough carbon dioxide. Pretty hard to find those environments on Earth, find CO2 limited environments, but you can. But more commonly is to find places where some of the other important elements of life are missing. Nitrogen, phosphorus, potassium, iron, so that we limit the amount of photosynthesis, and therefore we aren't creating or recreating the oxygen that's being consumed by the animals in that environment. And so in environments that have excess photosynthesis, meaning excess of this forward reaction, then they're going to build up oxygen. But remember, the concentration of a gas in water in equilibrium with the headspace above it is governed by Henry's law, and it's very hard to supersaturate the water with respect to a gas. So if we somehow had excess photosynthesis in a body of water, it was producing extra oxygen, that oxygen would percolate out of the water up into the atmosphere and always kind of be at the chemical equilibrium value. Does that make sense? And if somehow, right at that surface of that body of water, a whole bunch of animals got in there, maybe something got spilled in the water or something got added to the water, that was a food source for respiring organisms, and they consume a bunch of extra oxygen, they might for a moment lower the amount of oxygen in that body of water at the surface. But because of exchange in Henry's law, the oxygen is going to percolate in from the atmosphere and kind of balance it out. So right at the surface, when we're in contact with the atmosphere, it's pretty hard to get away from a concentration of oxygen that is governed by Henry's law. But if we get anywhere away from there and we change the balance of how much photosynthesis and how much respiration is happening, we're going to change how much oxygen is present. The whole point I want you to get out of this is that oxygen being present in its oxidized form, which means O2, molecular oxygen, that's the most oxidized form of oxygen that we can find typically in natural environments on Earth. There's enough oxygen present that makes the whole environment that is in oxidized, meaning all the other chemicals that have a choice of what oxidation state they can be in, typically take that highest oxidation state. There are a few examples where it takes more oxygen than is present in our atmosphere to promote stuff up to its highest oxidation state. A good example is chromium-6, which we make and we use in the lab. It's found in various settings and so forth, but it's not a naturally occurring form in any appreciable extent of chromium. Instead, that's chromium-3. But for most other chemicals, think about iron-3 versus iron-2. When you put a piece of metal out and it rusts, it's rusting to iron-3. Iron-3 oxide has got that brownish color, whereas iron-2 oxide wouldn't. And so the presence and absence of photosynthesis and the presence or absence of oxidized oxygen relative to reduced oxygen, which is what water is, okay, is going to set the chemistry of a whole bunch of other chemicals. And that's what we want to talk about today. We want to use oxidation state, half reactions, and the Nernst equations to define a variable just like pH that we call PE. Remember, P, when we write a lowercase p in chemistry, we mean the minus log of something. That's literally all P means. So pKa we've talked about, pH we've talked about, now we're talking about PE. Right, and so PE is probably of the three, the only one that you probably weren't introduced to previously unless you had some kind of geochemistry class. We're going to define PE in a second, right? But PE works kind of like pH, right? So when you think about pH as being the minus the log of the activity of hydrogen ions, right? That's what pH is. And when pH is high, because it's a minus log situation, when pH is high, like pH is 14, that's a very low concentration of hydrogen ions. It's 10 to the minus 14. So it's basically a basic situation. We can do the same thing with PE. When PE is minus the log of the activity of electrons in a situation, your electrons that are available to make these kinds of reactions go. So in fact, it takes electrons to make this turn into this. Where does it get the electrons? It gets the electrons from this. So electrons are flowing. In this chemical reaction, whether it's photosynthesis or reduction, but we're talking about, respiration. Respiration is taking oxygen and burning carbohydrates, taking electrons out of the carbohydrate to make oxidized oxygen into reduced oxygen. Okay, and in so doing, the reduced carbon is turning into oxidized carbon. That process requires a flow of electrons. The higher or the lower the PE, the more difficult or the more easy that is to happen. At low PE, because it's a minus log situation, means there's a lot of electrons. When there's a lot of electrons, it means it's easy to break down the oxygen into this. Okay? And a whole bunch of other chemical reactions. When PE is high, it's difficult to do. Okay, so this just kind of restates what I just said on another slide, but in a slightly different way, which is to remind ourselves that photosynthesis is the great oxidizing process for water. Okay, but it's also, whenever we write out a chemical reaction as an oxidation and a reduction, if one thing's being oxidized, so during photosynthesis, water is being oxidized to oxygen, something else is being reduced. We don't get something for free, so we have to reduce our oxidized carbon into carbohydrate. The cycle of life has developed that we as responding organisms take advantage of this and run this reverse reaction, but we couldn't do it if it weren't for the photosynthesis. So while it is true that we, as macrofauna, consume oxygen and we do respiration, and we can look out and we can see land plants that are doing photosynthesis, that the bulk, by a way large margin, of the production of oxygen and consumption of oxygen in natural environments is done by microorganisms, not by us. Okay, they're doing the same thing. They're basically following that same reaction. There's just way more of them. And so the evolution of our atmosphere since when the planet started to today is directly linked with the evolution of life, right? The development of life, the advent of photosynthesis has caused a series of changes in our atmosphere, which we'll talk about in the kind of third unit of the class later in the semester, but that has basically taken us from a planet that had a lot of carbon dioxide and no oxygen in our atmosphere to an environment where we have a lot of oxygen in our atmosphere and not much carbon dioxide. And we're working to try and reverse that with our global warming and so forth. But really, to be honest, when we transitioned from a planet that had conditions like this to conditions like that, we changed everything about the aquatic ecosystems and the superficial deposits that make up things like soils and sediments and surface rocks, because in the absence of oxygen, all the other chemicals that were formed, all these other materials that were dissolved in water, that were sitting in soils, that were sitting in sediments, were sitting in conditions like this, reducing conditions. And in reducing conditions, certain elements like iron and manganese, and sulfur, that can be reduced, choose to be reduced. And they behave chemically differently than they behave when they're oxidized. During the period of time, during the Archean, in essence, and coming out of the Archean, we started to transition into having enough oxygen in our atmosphere that we could change these conditions. And we see this in the geological record. And like I said, we'll talk about that later today. And for now, we're thinking about modern environments on the surface of the Earth. And the presence or absence has not anything to do with like evolution and the sort of slow churning of the clock that developed life from abiotic practices. Instead, we're just thinking about the relative proportion of things that take place that cause us to change the balance of oxygen. So basically, to make photosynthesis happen, you need to have light, you need to have carbon, you need to have nutrients, right? Nutrients being things like nitrogen, phosphorus, potassium, iron, cobalt. And again, we'll talk about the nutrients in more detail later. For now, we can just say that these are, in most environments on Earth, some combination of this and this are the things that mimic photosynthesis. There's pretty much always enough carbon around. Maybe when you get into the deep crustal parts of the Earth, where there isn't light anyway, so you don't have to worry about it. But pretty much everywhere else, we've got enough carbon. So it's a question of whether or not we have light, whether or not we have nutrients. And one of the things that humans do is enhance the concentration of nutrients in the environment. Right, so we have to think about, our role. For instance, every one of us goes through the bathroom every day, we flush the toilet, that stuff goes down. That's just nutrients being delivered back into the environment. There's way more nutrient loading into the environment in the Hawaiian Islands because of the population, especially the transient population, than there would be if we weren't all here, right? So just thinking about it from the level of the entire environment of the Hawaiian Islands, more photosynthesis has to take place to consume those nutrients, or those nutrients would build up in the water. And that's something we can look at. Say, oh, well, are we, because of our waste management practices and the presence of all these humans, have we been adding a bunch of nutrients to the water, and is that showing up somehow, either biologically or in material that's related to biology in sediments or what have you? We can't find that in some places, but in most cases we don't, because photosynthesis, if we add extra nutrients, photosynthesis just takes over, right? Because we also have light. But if we add our extra nutrients to a place that's dark, where photosynthesis can't happen, there's no light, then the nutrients are going to build up. And at the same time, the respiring organisms that are in that environment are going to consume oxygen and make the environment more reduced. There's a bunch of terms that I use sometimes for this, and one of them that I want to mention is that what we call fixed or reduced organic carbon. It's a fancy way to say carbohydrate, right? So that is this right here. When carbohydrate is present, it can be produced abiotically. There are conditions where that can happen on Earth, but not very much of it. But when it's present, it's a food source. It's a food source for respiring organisms such as ourselves. And when we have CH2O present, then animals are going to, or respiring organisms anyway, microorganisms in many cases, are going to consume it and pull down the oxygen. So the presence of food equals the presence of respiration, and that happens in a wide range of environments on the planet, a wider range of environments than where we have photosynthesis. Because photosynthesis requires light and fresh nutrients. We don't always have both of these two things in the right proportions to support life, to support photosynthesis. So in cases where respiration is happening to this food present, but photosynthesis isn't happening, oxygen gets consumed, and we go to reducing environment. So that's sort of how the cycle of life works. And a great place to think about where this might happen is in the deep ocean, right? We got little particles falling down all the time, dead organisms, fecal pellets. Those represent food sources for respiring organisms throughout the water column. So as those particles are settling, there's animals that are consuming that food, and they're consuming oxygen. But because we're in the deep ocean, we're allowing this reaction to happen without this one. We're too far down for light to penetrate, so there's no photosynthesis. So again, we can go to a reducing environment. So this is just another definitional thing to remind you of some two primary metabolic strategies that organisms take on the planet. Especially heterotrophs, organisms that get their energy from the environment instead of from food from the environment instead of creating it themselves, which would be called autotrophs. So we have aerobic respiration, which is using oxygen, and we have anaerobic respiration, which is not using oxygen. This can become really important today to understand the difference between aerobic and anaerobic. The two things don't coexist because the organisms and the metabolic pathways, which are enzymatically driven for this condition and this condition, are not mutually able to exist simultaneously. You either have this or you have this. You don't have both. So pretty much the way things have evolved on Earth is that when we have oxygen present, we have respiring organisms that utilize oxygen. And photosynthesis is replacing the oxygen or not replacing the oxygen, depending on how much photosynthesis is happening. But in any event, as long as there's a certain amount of oxygen present, about 5% of what we expect for total saturation with the atmosphere, then we're going to have aerobic respiration. But in environments where there's so much food that and not enough photosynthesis to balance it off, that organisms take the oxygen lower than that, and anaerobic really means the absence of oxygen. But it never actually goes away. Maybe some tiny fraction of a percent of it. It's actually present. But as we transition from having oxygen present to not, which happens effectively somewhere at about 5% of the saturation value, we go into anaerobic respiration. Okay? And this is a class of respiration that has many subclasses. Because it turns out some organisms will utilize other chemicals besides oxygen to liberate energy from carbohydrates, which again, remember, that's all we're doing in this reaction as an animal, as a respiring organism. We're taking oxygen and we're liberating energy from carbohydrates to run our metabolism. Okay, and we're doing that by taking oxygen and reducing it to water. So oxygen is accepting electrons, and it is oxidizing organic matter. So carbon dioxide is a byproduct of the oxidation of organic matter. And what I'm saying is that under non-aerobic circumstances, this isn't here, but some other chemical is. So that other chemical is being used by organisms to do the same exact reaction, to oxidize organic matter, make some water, make something else over here from the oxidized organic matter. We'll look at how that works in a second, but I just want you to keep thinking by analogy that aerobic respiration and anaerobic respiration, the part that's different is the thing here that's driving the liberation of energy from the carbohydrate. Okay. So this is the stuff that is in this Redox intro MP4, which is up on the website on Welding. This is a definition of what oxidation state is. It's some rules, which you can find in any chemistry textbook, right? And the oxidation state rules are simple if we've got an atomic ion, like magnesium 2+. The oxidation state is just 2+. Hydrogen +1. Oxidation state is +1. But because we're complicated when we have compound ions, right? Like SO4 2-. And we see that as a reactant somewhere, and we want to know, oh, you know, if something changing its oxidation state, we have to calculate the oxidation state of sulfur, the oxidation state of the 4 oxygens, in a way that when we sum them all up, their sum equals -2, because -2 is the charge on the ion. And so there are some rules to do that. And as I say, you know, you should watch that thing and go through it. In most cases, oxygen is just given a value of -2, as per where it is on the periodic chart in the 6th column. And but there are some cases, some exceptions where oxygen doesn't get a -2. For instance, when it's bound to itself, it gets a 0, as do all things that are just bound to themselves and only themselves, like nitrogen and N2, hydrogen and H2. Those are 0 for oxidation state. The only other case where oxygen isn't a -2 is when it's in a peroxide molecule. A peroxide molecule, like hydrogen peroxide that you might use at home, H2O2 or sodium peroxide, they're we won't talk about them very much during the semester. They exist. They exist in smog, for instance. But this is a pretty rare condition. But when it's in that, in a peroxide, it gets a value of -1 instead. The other rule that is a little bit like, I just want to make sure that you know, is that hydrogen is almost always a +1 oxidation state, except when it's a hydride, which is, in which case is a -1, and a hydride is when hydrogen is bound to a metal. And again, you don't see it very often. We don't see it in nature. We see it in the lab. But so this rule doesn't come to bear very much. And so when you're doing something like this, you see SO4, you know, we know the oxygen by our definitional rule, it's not bound to itself, and it's not in the peroxide. It's going to be -2. So there's 4 of them, which makes -8, which tells us that the sulfur has to be +6, right? Because -8 + 6 equals -2, which is the total on the whole thing. There's a couple of other kind of, you know, rules in here. Halogens are usually assigned a value of -1, except when they're bound to oxygen, in which case they can have different oxidation states. And in most cases, not all, but in most cases, when we're looking at group 1 and 2, those have +1 and +2 charges. You kind of invoke these rules when you're given a molecule that doesn't have any oxygen in it, and you got to figure it out, oxygen or hydrogen, right? And this is an example, like NaCl. You're like, oh, how do I do that? I don't have oxygen, which is how oxidation states are defined. I don't have hydrogen, which is supposed to be +1. But we know that our alkali metals are usually +1, and our halogens are usually -1, and that's how we can assign the oxidation state and make this situation. Now we know that's an ionically bonded salt, right? And so when we calculate oxidation state, and it tells us that was +1 and that was -1, that's actually a pretty good depiction of the reality, right? Of the circumstance where sodium is donated an electron to chlorine, and in that molecule, it really is roughly that this is a -1 charge thing and that's a +1 charge thing, and they are bound together ionically. If we go to a covalently bonded substance like this nitrogen oxide, NO, We look on periodic chart, we see nitrogen and oxygen are right next to each other. There's almost no electronegativity contrast. So that is actually a covalent bond, a very covalent bond. In covalent bonds, especially very covalent bonds, there isn't much donation of electrons to one thing or other. It's more like a sharing thing, right? However, we can still calculate an oxidation state. The oxidation state helps us in a bookkeeping sense to figure out how many electrons are being transferred in chemical reaction, regardless of whether or not the convention and the calculation is giving us a true depiction of reality. So in this case, oxygen again gets its -2 value. Nitrogen therefore has to be +2. It's a single molecule with no charge on it. And we know what our rules tell us about oxygen. So nitrogen comes out +2. So we don't actually think that in this bond that 2 electrons have been transferred from here to here. We don't see that in the bond. It's more of a covalent thing. But we can use this as a bookkeeping sense to understand if the relative oxidation state of nitrogen has changed throughout a chemical reaction. So this is just a simple chemical reaction. NO plus ClO minus, that's a compound ion, right? So it's got 2 atoms bonded together in an ionic form. And we can see that what's happening in this chemical reaction is that chlorine is changing from ClO to Cl minus, and nitrogen is changing from NO to NO2. Does anyone want to take a stab on saying what thing is being oxidized in that chemical reaction when we go from this side to this side? And what thing is being reduced? So in the simplest case, where we have molecules that have oxygen in it, the more oxygen, the more oxidized. So NO2 is more oxidized than NO because it's got more oxygen in it. That one's kind of easier, I would say. We have cases where the oxidation state changes, there's no oxygen to kind of hang the hat on. But in this case, we can say, look, this guy went from having 1 oxygen to 2. It is more oxidized. At the same time, this guy went from having 1 oxygen to none. It is less oxidized. Less oxidized equals reduced. Well, we can prove that using oxidation state. So what I've done here is I've calculated the oxidation state of each atom in each molecule up there on the board, right? And oxygen is given a +2 by definition, and over here this is obviously -1, but because this is a +2, oxygen -2, chlorine has to be a +1, right? For this thing to add out correctly. So chlorine comes out with a +1 because +1 -2 gives us a minus. So that's a case where chlorine, this halogen, is not at a -1 state. So that's why we can't always just assume when we say halogen it's a -1. In this case, it isn't. And in fact, this chemical reaction is one of the critical reactions that helps mediate the destruction of ozone in the ozone hole. So it's an important reaction that happens that we need to be aware. Up here, nitrogen, oxygen, we can calculate them out. It's a 0 molecule oxidation state is 0 overall. Oxygen is -2, nitrogen has to be +2. So when we look at all of our stuff and do the bookkeeping on it, we can see that the chlorine changed oxidation state, right, is gone from being +1 over here to -1 over here. And when one thing changes oxidation state, something else has to change oxidation state. We've already sort of decided that because of the molecules that we find oxygen in and the rules for how we assign oxidation state for oxygen, that none of the rules that would allow us to give oxygen anything other than a -2 value apply. So the other thing that must be changing is nitrogen. This is one of the critical things about writing out electron transfer chemical reactions. Not only do they have to be balanced for material and charge, like all chemical reactions, they got to be balanced for electron flow. If they're not balanced for electron flow, they're not balanced. So somehow, when this thing went from here to here and got reduced, and this thing went from here to here and got oxidized, electrons transferred between those molecules. That's how it works. That's the mediator of oxidation reduction. And that's why we use PE, the minus log reactivity of electrons in an environment, to say something about the propensity for this reaction to happen or not. Because each one of these chemicals is going to have a certain desire to be in its reduced or oxidized form in the presence of oxygen. And the proportion that we find is governed by an equilibrium constant. An equilibrium constant is defined differently depending on whether we're looking at a fully formed chemical reaction or a half reaction, which is written as either the part of the chemical reaction which is an oxidation or the part that is a reduction. The oxidation part is NO going to NO2, and the reduction part is ClO minus going to Cl. And we already know, because we've calculated the oxidation state, that 2 electrons are transferred to make that happen. This stuff here has to absorb 2 electrons to make that stuff. And this stuff has to liberate 2 electrons to make that stuff. So it's balanced. We can calculate that out here, that it's balanced for electron flow. So this is a mnemonic that I learned at one point. You can remember however you want, but what is an oxidation? What is a reduction? Oxidation is losing electrons and reduction is gaining electrons. So I learned it as Leo, the line goes GER, meaning lose an electron is oxidation, and gain an electron is reduction. I learned this as a chemistry student in the context of batteries. So I actually learned Leo, the line is goes GER, because lose electrons is oxidation at the anode of a battery, and gain electrons is reduction at the cathode of the battery. Nevertheless, if you can just always go back to this silly thing and say, what thing in my chemical equation is a Leo and what thing is a GER, you'll be able to figure out what's being oxidized and what's being focused. Okay, so there's that half reaction, that whole reaction. Here it is separated out into 2 half reactions, right? NO goes to NO2 plus 2 electrons. It's lost 2 electrons to do that. We know that from our bookkeeping. And ClO is absorbing 2 electrons and going to Cl minus. Hopefully you can see that if we just algebraically add those 2 equations back together, right, that the electrons are going to cancel out and we're going to be left with this reaction. The thing is, we can look these chemical reactions up in tables, these half reactions, and they have electrode potentials associated with them. This is where the Nernst equation comes in. The electrode potential is the voltage required to make this transition happen or not happen. And that voltage is basically can be related to the activity or concentration of electrons that are available in the environment, thus giving us this idea of PE. Because we can take these half reactions, take minus log of both sides, rearrange them, and come up with a term that's minus the log of the electron concentration, and figure out the PE of the environment just the same way we do for pH. Now, it turns out that when you look these things up in the tables, you find sometimes half reactions that look exactly like what you've written, and sometimes they're in slightly different forms. Like, for instance, there's water added or subtracted. So we actually find for this equation in the table is this one. It's still got NO going to NO2. It's still got 2 electrons being transferred, but it turns out that there's also a transition in water when that chemical reaction happens. Same thing for this other reaction with ClO minus making Cl. It turns out that there needs to be some interaction with water. Now, when we add these things together, the waters cancel out, the hydrogen ions cancel out, and the electrons cancel out, so we're still left with NO plus ClO minus goes to NO2 plus Cl, like that. But we found slightly different versions in the table of half reactions that we look up values for. So this is the Leo, and this is the GER, and you can tell that from half reactions, because lose electrons is oxidation always means that the electrons are going to show up in a product to the half reaction, and gain electrons is reduction is always going to show up in the reactants of the half reaction. Yeah.
Is it always written like that? So where the products are for Cl minus plus H2O, like where there's like a plus in front of it, is that always there?
Which one?
It's like above the, yeah, or the one to the left of that, of Cl minus.
Oh, this.
Yeah.
No, that's a mistake.
Okay.
Sorry.
Oh, no worries.
That's good that you're catching me. Yeah, no,
I think it's on the top one too, but I was like, I don't or like the sum of these two. Yeah, and then below that, it's like the same thing. Might have just,
you know, here?
below that. Yeah, all the way at the end on the right.
Oh, you're right. I don't know. No, you're right. That's just like me cutting and pasting.
No,
Bad.
that's okay.
Okay, I'll try to fix that and put it back up. Yeah, no, that is totally wrong. So now let's just talk about the Nernst equation for a second, right? This is the Nernst equation. Delta E, which is the electromotive force, which is a thermodynamic parameter related back to Gibbs free energy, but it only applies in cases where electrons are being transferred. And it's something we can measure with a voltmeter, basically. Delta E, which is the change of electromotive force driven by chemical reaction, equals delta E naught, some standard state, just like we have for all of our other variables like delta H and delta S and so forth. These are at 25 degrees C and 1 atmosphere. Okay. So the half reaction of some mixture of chemicals is a standard state half reaction. Okay. Plus 0.059 divided by n being the number of electrons being transferred, times log Q, Q being the reaction coefficient. It is written out exactly like an equilibrium constant, but we don't have equilibrium proportions. And if we go back to this reaction, and we look, right, and we say, okay, well, how many electrons are being transferred? In this particular case, it's 2, because we balanced our equations and stuff, so n is going to be 2. Okay, this is a simplification of several things. 0.059 is basically the combination of R, the universal gas constant, temperature, specifically at 298, okay, and Faraday's constant. So you'll commonly see this equation written out, but it only applies at 1 atmosphere and 298K. If we were to use it at 398K, this would be a different value. If we're using it, at some other value of T, it would be a different value too. But that's the only part about this expression that changes. Faraday's constant doesn't change with temperature, and the universal gas law doesn't change with temperature. But if we're calculating redox at things other than 25 degrees C, we have to pull back out. And I give you those equations in a moment. But for simplicity, I'm just using the standard form of the Nernst equation, which you've been given before, which is for 25 degrees C or 298K. So another thing, just like all these expressions like delta G equals delta G naught minus RT ln K, or excuse me, plus RT ln K. At chemical equilibrium, this value goes to 0. Okay. So when Q equals K, we can substituting K here and substitute 0 here, we get the simpler expression delta E naught equals minus 0.059 log of K. Okay, and we know what K is. In the case that we've been talking about, it's the reaction between NO2 and Cl. And so the driving force for this reaction tends to be the flow of electrons. However, another way to think about the driving force of this reaction, where there's a small amount of this and a large amount of something else, which is controlling the availability of electrons, which is what makes this happen in the first place, is that this, we can force this reaction to happen by putting a lot of product reactants together, or we can see how the proportion of products and reactants fall out when we let something else control the oxidation state. And in nature, that something else is the present reactions of oxygen. So adding oxygen to an environment or not, right, is going to determine how much this reaction happens, and all sorts of other redox reactions. So a great place to find environments that don't have much oxygen are in the interior of the earth, the mantle. Go down to the core, there's even less oxygen. Those are places where chemical reactions that favor the reduced side of an equation are more common than chemical reactions that favor the oxidized form. When we get up here at the surface of the earth with all the photosynthesis, that's where we start to get to oxidized settings. And interestingly enough, as far as we know, we are the only planetary body in this solar system that has photosynthesis, that has oxygen. So the fact that we're living in this oxidizing environment, we've got all these respiring organisms and we've got all these chemicals that are in their oxidized form is weird. It is totally different and unique from everywhere else in the solar system. And perhaps until we discover life on some other planet, perhaps it's unique amongst all the solar systems. We don't really know. We don't have an answer to that. And that's just one of the things that people look for, one of the biosignatures when they're trying to explore other worlds, even remotely, is there any indication that there's some oxygen present? It's really hard to make oxygen thermodynamically with the mixture of chemicals that we typically have in our planetary system. We need to have biology drive it. And so it's kind of useful to remember that the oxidized condition that we have here on Earth is unusual. We're all used to it, but it's unusual. So these are some other chemical relationships. Okay, and so one of them is that the delta E, the EMF, the electromotive force that drives these reactions, is just related to the Gibbs free energy of reaction by the number of electrons flowing in a Faraday's constant. That's what that funky little F is. You see it written slightly differently in different books. That's the fanciest F font that I have. But you know, he has a slightly fancier F in the textbook. But it's Faraday's constant, which you can look up in kilocalories, you can look it up in joules, you can look it up however you want. And this is an important relationship because we remember, we all know that the equilibrium constant is related to the Gibbs free energy. Right, so Gibbs free energy has a certain value, equilibrium constant has a certain value. And those are things that we can calculate really easily and go back and forth. But because for electron transfer reactions, there's a simple relationship between Gibbs free energy and the electromotive force, simply being the normalized by the number of electrons being transferred to Faraday's constant, we can use all the same formalism that we use for equilibrium constants when we measure energy using E instead of with G. And this is a simpler way to measure energy transfer in electron transfer reactions. But it doesn't mean we couldn't use G, we could. But the one thing we can't do is use E for chemical reactions that don't have any electrons being transferred. Because there won't be any potential, because there won't be any electrons being transferred. It'd be like trying to make a battery out of two things that don't want to react with each other. And then these are just some other relationships. The first one is, what is PE? I defined it before, but now remember, it's just a minus the log reactivity electron. Okay, well, it is the log of the equilibrium constant divided by N, or as we've seen it before, we know how it's related to delta G. The only difference between this and in the past of these natural logs, which is doesn't require this extra factor of 2.3. But when we're talking about log base 10, we got to add that extra 2.3. And some of these other relationships are just algebra on these two expressions. But this is an important one here to note that we're going to talk about PE in a second, which is the minus log of electron activity. It's just related to the electromotive force by a factor of 0.059. And whether we're talking about any PE or non-equilibrium sense or a standard PE, it's just a simple relationship. So sometimes we're going to see diagrams of PE versus pH for water. And sometimes we're going to see diagrams of E versus pH. And they're only offset from each other by a constant. Okay. In some textbooks, E is written out as E with a little H next to it. Okay, and that's because just like everything else in thermodynamics, we have to pick something that we set as a standard defined value that we compare everything else to. And for electromotive forces, we set them relative to something called a standard hydrogen electrode, which is the reaction between hydrogen ions and hydrogen gas. And we say that that has an electromotive force of 0. It's like a definition. And so that's why oftentimes you will see, like I say, a little H here. I don't put in the H because I don't want to make it extra confusing. But in tables, you will commonly see people talk about EH instead of E. And it's literally the same. Okay, so we can take this reaction, the Nernst equation reaction, and, you know, as I say here, we compare it to the standard hydrogen electrode, and then we can calculate for every other half reaction that might react with this thing, how many volts are going to transfer, whether it's positive or negative, right? Electrons are either going to flow in or out of the material, and that's going to give us a value for E or EH, for every single half reaction that we can write. And they're all relative to this one being 0. And those are in table. And so that's a pretty straightforward thing. And hopefully that's all stuff that you've seen before. But now I just want to talk for a moment about what is PE actually. Okay, so PE is the availability of electrons. It's defined as the minus log of the electron concentration. And we call a system that has a specific value of PE poised. Poised is just like buffered in an acid-base sense. Okay, in an acid-base sense, when it's buffered, you've got a relatively equal proportion of conjugate base and acid. In a PE sense, when the system is poised, we've got a relatively equal concentration of oxidation with these chemicals. Okay, and so you can think about it directly analogous to pH. pH is the minus log of the hydrogen ion concentration. PE is the minus log of the electron concentration. In reality, neither of these things exist in the environment. Right? We don't really have free hydrogen ions, and we don't really have free electrons. Instead, we have chemical forms of other things that represent having a lot of hydrogen ions, which means low pH, and having a lot of electrons, which means a low PE, or not having very many hydrogen ions, and so having a high pH, and not having very many electrons, and having a high PE. So here at the surface of the Earth, in the presence of oxygen and photosynthesis, we have a high PE. Because all that oxygen is present, it's not allowing there to be many free electrons available. pH can vary, right, from place to place. We've talked about this before, but most of our pHs in natural waters are set by the amount of carbon dioxide that's present, which puts us in a range kind of on either side of 7, somewhere between 5 and 8 or so. And that's the natural range of pHs at the surface of the Earth. PE can vary more than that on the basis of whether or not we have, for instance, the requisite for photosynthesis, which is the light and the nutrients. We can see more variation in PE than we can in pH. And this is why it's important, because other chemicals change their chemical form on the basis of that. So both these things are conceptual, okay? pH, we think about in terms of acid base, and PE, I want you to think about it in terms of oxidizing and reducing or redox, right? So an environment where PE is high, where PE is high, is oxidizing, and the environment where PE is low is reducing. So if you now take another half reaction, like the half reaction of iron reacting with hydrogen, remember this is just a standard hydrogen electrode, which is a value of 0. But we can look up that iron reduction reaction. We can see this a reduction because iron's going from +3 to +2. We can apply our oxidation state rules and see that iron has absorbed electrons in the process of that reaction. We also see that the standard hydrogen electrode is written as an oxidation because it's going from hydrogen gas, hydrogen bonded to itself has an oxidation state of 0, to 2H+. That means that those hydrogens have lost electrons, right? They're being oxidized. So the LEO in this reaction is hydrogen gas going to hydrogen. The GR therefore must have to be iron going from +3 to +2. So I can look up in a table the half reaction. It is this thing here. It's got a value of 0.77 volts. If I want to add these two things together to make that equation up there, I have to multiply both of them by 2, and that is to make it balanced for the flow of electrons. But I can also write out the equilibrium constant expression for not only the whole reaction, but the half reaction. So here I've written out the equilibrium constant for this upper half reaction, okay? And then I've just rearranged it. I put the electrons, I put that bracket E minus stands for just electrons. I put that over by itself, and I moved all this stuff over underneath the K, okay? And so that's how it can be expressed. And then I take the minus log of both sides, right? And this is just the algebra of log. And this thing here is PE. And this thing here is PE naught. And this is just a ratio. Whereas in the equation for acids and bases, this is the conjugate base over the acid. In this case, this is the reduced chemical as the oxidant. But there's still that same analogy. So a system is poised, just like a system is buffered, has value of this thing that's roughly equal, so this becomes basically 0, so then this PE just becomes PE known. Yep, got everyone? Okay. So you can also, you can flip this. Oxidize will reduce the change the sign, right? That's just like another algebra of logs. And the other thing that you don't see in this equation up here is the flow of electrons, because the way it's written out up above, it's just one electron being flowing. But in the more general sense, with another equation where we have multiple electrons, that is where they would show up. They show up in front of that ratio of oxidation. So the next thing to think about, and I don't know, we don't have a ton of time left, but I'm going to keep going, is the oxidizing and reducing limits of water. Water being present on the planet means that the environment isn't so oxidizing that water decomposes into oxygen. Right? If our environment were super oxidizing, we would lose this stuff. At the same time, if our environment were super reducing, and this does happen in the interior of the Earth near the core, where water decomposes into hydrogen. That sets up two chemical equations that when we have water present, we know we have to be somewhere in between these two oxidation limits. This is just a standard hydrogen electrode. It's written out in a slightly different way, but it boils down to this reaction. And this we know has an electromotive force of 0 and a PE of 0. This has a value too. Okay, so I'm going to ask you to look through the notes. I'm going to go through each diagrams next time. Hopefully, we'll see how far I get. But we want to use the stability field for water, and then look at the way other ions behave in water, to say something about how oxidized or reduced that environment is. And then what we'll finish up with is seeing how organisms control it. And then that will help us set the stage for using PE as an environmental variable for the rest of this unit, where we're talking about the hydrologic cycle and the hydrosphere. But we have to understand kind of the mechanics of how all this works. So I will leave you with that there. And then if we end up getting through that stuff, and then hopefully we'll have time to also talk about organic chemistry, which it turns out organic chemistry is the food source for this chemical reaction up here. It's what drives the presence or absence of reduced carbon in the environment, which is the other side of the equation along with oxygen that sets oxidation state. All right.